All right, so we'll continue our discussion on verification algorithms. So last week we have seen examples of how we can verify a yes instance easily if we have a certificate. So in general, a verification algorithm has two parts. So we have, of course, we have ordinary input. That's a normal input. But other than this, we also have a structure or a string. So this one is a structure or string. Of course, in general, it's a string. Other than input, we have something for to help us. That's called a certificate. If you just give us an input, it's difficult to determine whether it's a yes instance or not. But now we have a hint. So we use a structure or string as a hint. So formally we call it a certificate. With the help of a string, the certificate, then the task of convincing someone that this instance I is a yes instance become much easier because we have the certificate. That's the key difference between verification algorithm and ordinary algorithm. So we have a hint now. All right. So typically, this certificate is just a solution to the instance. Because for many problems, when we specify the problem, we have input and question. Typically, inside the question, very often what we ask whether exists some structure S that satisfy a particular property. Or maybe a bit bigger. So typically this question. All right. So input part, for example, it's a graph problem, maybe a graph G, and maybe and a natural number K, for example. So that's the typical way of how we specify a problem. And certificate usually is this structure that satisfy property PI. So typically it's the structure as satisfying P. So in other words, PI holds. Sorry, PS holds. All right. So very often for many problems, for example, the vertex cover problem, and say we're looking for at most k vertices that cover all edges. So a certificate will be k vertices that cover all edges. Clique problem, we're looking for a complete subgraph on k vertices. So certificate will k vertices that form a clique. The Hamiltonian cycle problem. Is there a spanning cycle in the graph, so a cycle containing all vertices, or whether we can visit every vertex by following cycle exactly once? We visit every vertex exactly once by following cycle. Then the certificate will be a spanning cycle, a cycle that contains every vertex of the graph. All right. So typically, it's very simple. The certificate. All right. Okay. Then we say that the certificate, verification algorithm verifies this particular instance if there exists a certificate, such that when we give both I and its certificate as input to the algorithm A, then algorithm will indeed verify it. It will say yes. That's a function of verification algorithm. So compare with you try to convince some people that certain property holds. So you give your friend maybe evidence, all right? So that evidence is certificate. The purpose is to convince your friend that the property certainly indeed holds. So once your friend gets the proof or the evidence, then your friend can easily verify it. Indeed, this is true. So that's the purpose of verification algorithm. So intuitively, of course, verification is much easier then come up with evidence or come up with certificate. We don't need to care about how we obtain the certificate. So you can assume a certificate is given. So we only need existence. All right. Now, an algorithm is a verification algorithm for a particular problem pi. If A verify every yes instance of the problem, so it's not symmetric. We only need to verify yes instance. If the instance is no, then we don't care. So verification is for yes instance only. That's very important. It's not symmetric. Because to verify no instance usually is much more difficult. All right. So suppose you want to prove you are a millionaire. It's possible. You can just show your friends you really indeed have $1 million, right? So you're a millionaire. But how can you show the friends that you have no money? It's much more difficult. No money at all. How can you prove that? You cannot just show your friends your bank book. Maybe it has zero balance, but you may have some money hidden somewhere. Who knows? Maybe 1 billion, right? So it's not symmetric. What we need is to verify yes instance. So for every yes instance, we're able to prove it. Indeed, it's a yes instance. Okay. All right. So that's the idea of verification algorithm. Now, based on this one, we can define a new class called NP. Class NP contains all decision problems that admit polynomial time verification algorithm. So this one is defined to be all decision problems Remember, we focused on decision problems. So all the problems we discussing will be decision problems. So that's meaning of class NP. All right, so meaning is, so for every yes instance, so for every, let me, for every yes, so exists a certificate. So every yes instance have a certificate. All right, such that we can verify the yes instance in polynomial time given both I and the certificate as input. So input actually should be both. So instead of just the ordinary input I. So that's the meaning of verification algorithm. And now we can define a class of problems called NP. So in comparison with class P is defined in terms of how fast we can solve the problem. Now class NP is defined in terms of how fast we can verify this instance of the problem. So proof that the problem has a solution is easy. Okay, so problem in P means we can solve the problem easily. Now, problem in NP means we can verify that a problem indeed has a solution. Okay. So that's the difference. So intuitive verification is much easier than find a solution. So that gives us very important connection between these two different classes. So we always have P is contained in class NP. So whenever we can solve a problem, verification algorithm for problem inside P is very easy. We don't need to give a certificate because we can solve the problem in polynomial time. So certificate can be empty. So it's trivial that P is contained in class NP. All right. So meaning is here, P means easy to solve. And class NP means easy to verify. Maybe it's okay. Maybe write more closer to the circle here. Okay. So this one means easy to verify. All right. So for most natural problem, it's very easy to see that the problem is inside NP. For most of the problem you encounter in practice, but it's not always the case. Let me give you some example, a couple of examples that sometimes verification may be difficult. So otherwise, you may think that every problem is inside NP. It is not the case, of course. All right. So let me give you maybe 2 or 3 examples to enforce the notion of verification algorithm to give you a better understanding of the class NP. Okay. So let's consider the following. Maybe. Oh, it's okay. It's maybe I draw it more like a squid. Okay, I give you a graph. It's a 4x4 grid. All right. So I want to convince you that G has a perfect matching. So that means I can pair up vertices in a perfect way. So all vertices can be paired up. So in terms of problem, we can ask the following. So perfect matching maybe. So input graph G. And question, does G have a perfect matching? Have a perfect matching. All right. So it's very easy to see a certificate. A certificate is just a perfect match. So certificate for this one. So of course, in this case, input will be G. So we can write G. So certificate for graph G. This one is just a perfect matching. Any perfect matching will do it. So it's really trivial. All right. So for example, we have so you can easily check. Every vertex is matched up. So indeed, it has perfect matching. So I can easily convince you. Checking for you, for verification algorithm, time for checking is very quick, linear time, of course, right? You just need to check. These waved red edges indeed form a perfect matching. Okay, now what I'm going to do is construct a new graph by removing 2 vertices. So new graph will look like this. This is our new graph. Okay, now I want to convince you that this graph has no perfect matching. So let's say G prime. I want to prove that G prime has no perfect matching. All right, so now the problem we are considering, so this one, in terms of perfect matching problem, is a no instance. It's a no instance. So when we talk about verification algorithm, we don't care about no instance. All right. However, we can change the problem. Instead of a perfect matching problem, I consider a new problem, say called the no perfect matching. So that's our new problem. So instead of a perfect matching, I will consider no perfect match. Okay, so that's our new problem. Then for this new problem, this one is a yes instance. If it's indeed has no perfect matching. All right, now in order to show that we can verify that G prime has no perfect matching polynomial time, I need to give a certificate. So what will be a certificate for this problem, for this particular instance? Now, the definition of decision problem are very general. It is not necessary to say that in question part we always ask questions, is there a structure with property P? So here it's just a yes, no answer, and yes, no question. So here it's a perfectly defined. The question here is a yes, no question. Does G have no perfect matching? But we don't have any structure involved. You can see structure involved is S. So that's perfect matching. But the question is asking no perfect matching. So then what would be structure that can be used as a certificate for this G prime? Now you see, it can be very subtle, can be difficult, maybe not obvious. For most problems, it can be obvious, but for some problems, it's actually not obvious at all. All right. So in fact, for this one, a certificate will be a two coloring. So what we can do, we can color vertices of this graph, say by red and green, maybe. Okay. All right. So I give a coloring red and green so that any two adjacent vertices receive different colors. I will argue that this coloring is a certificate. That certificates that G prime has no perfect matching. The reason is, if we count number of red vertices and the number of green vertices, we see that they're different. Number of red vertices will be 8, number of green vertices will be 6. Now that will be enough to show that G prime has no perfect matching. Because of the particular way of we color vertices, any edge inside the matching must match a red vertex with a green vertex. So that means if G prime has a perfect matching, then number of red vertices will be equal to number of green vertices. So, but this is not the case. So I think I can easily convince you in this way that a G prime indeed has no perfect matching. All right. So the certificate in this case will be a two coloring, a prop two coloring. So a two coloring where adjacent vertices receive different colors. So in this case, that will be a certificate for yes instance of no perfect matching. All right. Is that okay now? Is it clear? So it's not trivial. Sometimes it can be complicated. In the notes, there are the example for this problem in general, what will be a certificate for no perfect matching in general? Yes, certificate can be two coloring. Actually, should be a two coloring. Just these two numbers are low are not enough, because depends on how you color them. Because the way we color the graph is particular. If I color vertices in this way, sorry, suddenly. Then we cannot use the argument. So the coloring has to be special. In this case, adjacent vertices must receive different colors. So these two numbers alone will not be good enough. It should come together with the coloring. All right. Okay. In general, the certificate of no perfect matching actually it exists, but it's much more involved. Actually, it's based on the classical theorem of Tata. It's a classical theorem of Tata. So let me briefly mention it. So that's a particular graph. So we have a particular way to prove it. But in general, this one will not work. Coloring will not work. So general certificate for this instance of this no perfect matching problem. This one very based on classical theorem of Tata. It's very involved, not easy at all. Okay, there are some deep theory here. Based on his theorem, it says a graph has a perfect matching. So we'll remove vertices inside the V prime, and then we'll break the graph into pieces. And then some pieces contain even number of vertices, some contain odd number of vertices. So the containing odd number of vertices called odd components. So it's really based on this classical theorem Tata. So let me show you what it means. So we can remove some vertices. Say this one is V prime. So this one is V prime. Once we remove it, the graph may be broken into pieces. All right. So some piece may contain even number of vertices. So origin is adjacent to some edges here. So some components here maybe. So that's one even number of component vertices maybe. So that's one piece. And another piece maybe here. So this one contains all the number of components. So that's all the components. Contain all the number of vertices. That's called all the component. All right. So this one has some connection here. Maybe look like this. And some odd, maybe another odd component. And so on. So some may be even. All right. What Tata theorem says is in order for graph to have a perfect matching, number of all the components can be not more than number of vertices in the cut. So the reason is if a component contains even number of components, even number of vertices, it's possible to match vertices inside. So we can do things like this. But for components that contain all the number of vertices, at least one vertex. So some can be matched inside, but at least one vertex must be matched with a vertex inside V prime. So we have to use at least one edge. So this one have to use at least one edge. So if we have more than V prime vertices, that some cannot be matched. So if in this case, so we can match this one, but now this one, there is no way. So that's the idea behind Tata theorem. One direction is trivial, as I explained. Another direction is very involved. So a certificate will just be a cut with this property. That will be a certificate. Okay. So see, sometimes it can be very involved, as in this case. Okay. So another case, sometimes it's, we even cannot find a certificate. So actually, some problems do not belong to NP. For example, the following problem. So give you a graph and ask you whether the graph contains at least k different minimum spanning trees. So that's a kind of so-called counting problem. We count number of different spanning trees. So in this case, how can you give me a certificate? Of course, if one or two spanning trees, if maybe k equal 2, then you can just give me 2 minimum spanning trees as certificate. But this k can be large. Maybe k can be even exponential, maybe 2 to the power of n. So it cannot give me all minimum spanning trees, 2 to the power of n minimum spanning tree as certificate, because at the time it takes to verify the algorithm will not be polynomial. So for polynomial time verification algorithm, it's naturally put a bound of certificate size. The size of certificate is at most bounded by a polynomial of the size of input, because we want to verify the problem in polynomial time. So in this case, actually, the problem does not seem to be in NP, because we cannot have a certificate of polynomial time, or at least we don't know how to obtain such a certificate. All right. Okay, I think that's good enough for the idea of verification algorithm. So intuitively, verification is much easier than finding a solution, and the way to have this relationship because between problem inside P and problem inside NP. All right. So now our original task is to find a seed problem for hard problems. So our original target, our objective, this is our original task. We try to find the easiest hard problem as a seed problem that can be used to prove that other problems are difficult. However, what we come up with is we identified some problems that's easy to verify. So seems to be totally different things, right? Now, what can we do? So actually, the reason for define this class NP is really for this objective. So this will enable us to identify some problem inside this one. Now we want to identify some problem inside. So this problem pi will be maybe put a stop because see the problem. We want to find the problem inside NP, but not P. And this problem is hard to solve. Then this pi prime will be good enough for our seed problem. So theoretically, all right, now we know where to look for this. Our seed problem is inside NP minus P. So theoretically it's inside, but how do we find it? So we know there is maybe a very large piece of diamond, maybe in the mountain, a mine site in cross the river over there, okay? But how do we find it? So we know where to, we narrowed the region to find this problem pi star, but exactly where it is. So that's the next problem we are facing. So what we do need is to find the problem inside NP minus P, and it is hard to solve. So how can we show that a problem is hard? So how can we show a problem is hard to solve? Actually, we have no idea at all how can we prove it. We know that we're looking for a problem that's hard, but among hardest problem, the hard problem is easy. Yeah, so how can we show that a problem cannot be solved in polynomial time? It's almost impossible. No one knows. If we knew it, we do not need to go through all these things. We just give a problem pi star, we just prove it cannot be solved in polynomial time. Unfortunately, no one knows. It's too difficult. That's why we use this complicated detour in order to reach our objective. So how can we prove that the problem is difficult? Now again, going back to our previous discussion of how to prove that you are famous. So how can we prove that a person is very famous? A person is famous. So a particular person is famous. So Ethan. So how can we prove Ethan is very famous? In Hong Kong at least. Ethan Chen, okay. I think a lot of young people really like him. Like for my generation, maybe Lao Dou or Andy Lau sounds more familiar to me. Okay. So anyway, how can you prove that Ethan is very famous? In daily life. So why you say that Ethan is very famous? Is famous? Exactly. Appearance on you. Sorry, I saw some. Yeah, it's close. But what do you mean by appearance? What else? Some other famous people. So if you can say that everyone knows Ethan, is that good enough? I think that should be good enough to convince you that Ethan is famous. If everyone knows it, it's better than what you said, right? Some other famous people. Yeah, Yeah, here actually you get into a cyclic argument. Some other famous people. So how can you prove that these famous people are indeed famous people? You say some other famous people know these people. But then what do you know by what do you mean by famous people? You get into cyclic argument. Right? Okay. So here, this one is not cyclic argument. I say that everyone knows ether. That's good enough. Right? So what happens is the following. So everyone knows ether. So an arrow indicates knows this relation. All right, so we can follow this idea. How can we say that a problem is difficult? So everyone knows this problem in a sense that every problem can be reduced to this problem. So we really follow this idea. Okay, so what happens is this. So we follow this idea. So let me erase this red ones. So erase everything, okay? So we have much more room now. So we follow this idea. So how do we say that this problem is hard? So we have a technical term called NP hard. So that means every problem inside NP can be reduced to this problem. So that's exactly the same as how we prove that Ethan is famous. So here, each arrow indicates polynomial reduction. So this one, or in other words, it's all written in this way. So here the problem pi. So this pi can be reduced to pi star, or in this notation can be reduced to pi star. All right, so we follow this idea to define that the problem is hard if every problem inside NP can be reduced to this problem. Make sense? You agree? Okay, good. So now we can have a technical definition. Maybe for the time being, I use a pi star. Okay. It feels more like a fish instead of alpha. So that's the notion of hardness. A problem hard if every problem can be reduced to pi star. So what's the implication here? So that's the implication is if pi star can be solved in polynomial time, then every problem okay, take some time for the statement. So the problem pi star has a property that this particular problem, a single problem, if we can solve it in polynomial time, then every problem in NP can be solved in polynomial time. So number of problems in NP, actually even in practice, known problems we use in daily life. So will be thousands of problems. In theory, there are infinitely many, but in practice, at least thousands of problems. So this particular problem, pi star, has this very property. If we can solve this single problem in polynomial time, then thousands of problems can be solved in polynomial time. So you see, this property is so strong. So it's a very good evidence that it's very, very unlikely that pi star can be solved in polynomial time. Because once we can solve it in polynomial time, then so many problems can be solved in polynomial time. It seems like impossible. That's why that's good enough to view this one as very hard. That's very solid evidence. So it's not absolute evidence, but it's good enough, very, very strong evidence that the problem is difficult. All right. So we can identify some problems that are difficult. Theoretically, we define problem to be very difficult if it has the following this property. All right. Now, next thing is we can say a problem pi star is NP-complete. Now the word complete comes if the problem is inside NP and is NP hard. All right. Now a problem is NP hard. The problem actually can be outside here. May not necessarily be inside NP. So all problem inside can be reduced to this one. That's what we mean by NP hard. Now, if the problem is inside, then the problem is called NP complete. All right. Okay. Now, the word we have is the following. Then we can define the class of NP complete problem. We can define a new class. Or maybe I just say pi is NP complete. So meaning of NP complete is it belongs to NP and NP hard. All right, now the word of NP look like this. I thought I should write closer to the circle. And we have easy problem here, and now we have difficult problems here, NPC. So these stand for actually most difficult problem or hardest problems. All right. Okay, the biggest or prominent open problem in computer science is whether these two classes are same. This is the most famous open problem in computer science. Maybe someone in class can solve this problem in the next 5 to 10 years to answer this question whether P of equal NP or not. And most people believe they're different. But no one knows how to prove it. All right. Okay, so I think it's time to have a break. After break, we'll continue our discussion. All right, okay.